Hello, everyone. This is Spencer Snowling from Hatch, and I'm here today along with my colleague Nick Piccolo. And today we're going to be talking about simulation-based optimization for plant design and operation as today's webinar. We're going to be focusing on how to use the optimization tools that are there in GPSX. So after you've built your model and calibrated it, these are simulation tools that you can use to perform analyses with. And we wanted to highlight some of those ones that are a bit more on the advanced side and ones that you might not have had a chance to take a look at yet. So today is going to be a bit of a demonstration heavy version of this. We actually have four desktop demonstrations lined up and ready to go. I'm going to be presenting a couple of the simpler ones, and then Nick is going to come in a little bit later on and talk about some of the more advanced tools that we have for doing dynamic analysis. So one thing I will mention, as I always do, is that if you have any questions, please feel free to type them into the questions panel at the in your GoToWebinar dashboard. You can just pop that out, type those in. We'll see those and collect them as the webinar goes on, and then we'll hang around at the end to answer as many of those as we can. Okay, so the plan for today is I'm going to talk a little bit about numerical optimization, just a general background on what the concept of it is. And then I'll move on to talking about the various types of optimizer tools that we have in the GPSX software. I'm also going to show you how to set up an optimization in GPSX using our sort of built-in simple optimizer tool. And then run a couple of those demonstrations, as I mentioned earlier, a couple of typical types of optimizations that you can run on your plant designs. And then Nick will have a couple that he's going to run as well. And then we'll kind of finish up with some tips and advice for setting up your optimizer. And then, as previously mentioned, we'll hang around and answer some questions. All right, so numerical optimization is really there so you can actually make your plant design better. Optimization is basically taking an action to make the best or most effective use of a situation or a resource. So for something that is a complicated system, like an activated sludge plant, there are lots of degrees of freedom, lots of adjustments and things that you can change, tank sizes and operational parameters. And so optimization is a really good tool where you can sort of use these tools to improve and make some decisions about what some of those parameters should be under the most optimal settings. So there's lots of different wastewater process optimizations that could be done. You could focus explicitly on trying to get the highest quality effluent possible, get those really low concentrations. Or you could say, I'm fine with the concentrations I got, but I really want to optimize the plant to lower my energy usage, to reduce operating costs. Or maybe for you, the optimization is neither of those. It's somewhere in the middle, neither the best quality effluent or the lowest cost, but I want to make it the most robust, to make it such that it can stand up well to dynamic events like a wet weather or a slug loading of COD, for example. So really, the optimization is a very open-ended question, and it really depends on how you define it. What is the focus of what I want to achieve? You're going to have to ask yourself that question, and we'll go through the steps that help you determine what it is that you want to do and how to set up the best objective function in order to achieve what you want. So modeling is often, a key tool in carrying out an optimization study at a water reclamation facility. Usually these things are done by hand, by making small changes and rerunning your simulations, doing some steady state sensitivity analysis, for example, small changes in order to try and explore a particular, region of operation and see how the plant behaves in that area. So the numerical optimization algorithms that are available to you in GPSX really just kind of automate this process. They perform a search to find the best answer amongst many different combinations of answers, right? So if I have three parameters, it searches with those three parameters simultaneously and tries to find the best set of those three things together at once. And doing that with many simulations in order to achieve a specific objective that you have defined. So, our human brains are designed kind of work really well with one dimension at a time. but these optimization routines can do it sort of multi-parameter research in a reasonably effective way. So it's using a sophisticated search algorithm or algorithms that basically seek to find the most optimal set of parameters that achieves a given objective. And as I mentioned earlier, that objective can be many different things. So the user must have to decide what it is that they want to focus on. Is it cost? Is it robustness? Is it effluent quality? And then specify which parameters that you were going to give control over to GPSX. So these choices of these two things are extremely important, as we'll discuss later in the webinar. And you need to be able to make sure that you've reflected the thing that you want to achieve correctly in the equation that you are setting up. So the objective is often to maximize something like gas production or minimize something like cost or energy usage. So you need to pose the correct question in the correct kind of way. So what will happen is then the algorithm will search within the permitted boundaries to find the best solution, the best set of input parameters that you've let it have control of in order to get that objective there. So, and when I say permitted boundaries, there's always a certain amount of constraining of the problem that you're going to want to do as well. So in GPSX, you'll see that we typically have two uses for these optimization routines. The first one is parameter estimation. So in that case, what you're doing is you're saying my objective is to fit the model to these data points, to reduce the difference between what the model is showing and what the data was that was actually measured. So this is parameter estimation. You can have multiple sets of parameters that you're going to adjust simultaneously in order to sort of pass that line through those data points. And this is actually a screenshot from one of our tutorials where you'll see that happen. The more common use, and I think the more valuable use of the optimizer tools, is to do process optimization. So rather than giving GPSX control over something like one of those calibration parameters, you would instead say, find me the best set of recycle rates and DO set points to achieve, a really good setup for my plant. So this is where you're going to be, it's actually mathematically the same thing, but here it's about the choice of the objective function and the choice of the parameters that you're going to let it have control over. So here in this particular example, both of these, by the way, are from our sample layouts that we have in GPSX. We're reducing effluent total nitrogen, and we're giving it control over these 3 dissolved oxygen set points here, and you're seeing that it's making an anoxic zone, and that is reducing down the total nitrogen. And we're going to run an example just like this as a demonstration here shortly. So typical things, I just put together a few different types of things that you could do. For example, decide on the best anoxic zone fraction in your MLE system so that you can achieve the lowest total nitrogen. Doing total nitrogen is always a really interesting one because the optimizer needs to find that sweet spot so that it's doing enough nitrification and then enough denitrification in order to minimize total nitrogen. You could also do a dynamic one where you give it control during a wet weather event and allow it to control bypass fractions or step feeding fractions in order to achieve the fewest solids washed out, the least amount of solids that get washed out during that wet weather event. You could also have it do an energy cost analysis and say, give me the DO set points and recycle pump flow rates that minimize the amount of cost that we're experiencing, but I still want you to also meet the effluent targets. You have to put that constraint in. And also chemical dosage rates. That's another example. And that is, in fact, the one that I'll be showing you here first. So when I want to set up a numerical optimization, there are basically 3 steps in the process. The first one is to choose your target objective. So one or more model outputs that will be either minimized or maximized or matched to real data, et cetera, et cetera. These are places where you want to construct the objective that you're trying to achieve by selecting a certain number of model outputs that you want to use in the evaluation of how good my optimization is. The next step is to choose the optimization parameters. These are the model inputs that you are going to allow GPSX to control. So the algorithm will take control and start replacing the default values that you have entered with the ones that are determined by the search algorithm. And it will run simulations one after another, making adjustments to these values until it starts to see some improvement in that objective that you have defined. And then after a while, it'll keep searching around and doing its thing, and then eventually it'll converge to an answer. And then the values that are showing at that point are your best optimized answer. And then the last step, the third step in that process, is applying constraints. So that is actually in two different places, one being the minimum and maximum bounds for the optimization parameters. So just to go back to the previous slide briefly, how high and low do I want them to be able to allow that to happen in the search routine? So those must be applied to the limits, apply those limits to the optimization parameters. And then any other constraints that you want to apply to anything else in the model. It doesn't even necessarily need to be part of the objective function, although sometimes it is. But often it is sort of the things that I need to bound the performance of this facility within a certain range. So one of the most obvious examples of that is I need you to bound it such that my effluent still meets all of its limits. If you were to just turn on an optimizer, say reduce energy as much as possible and didn't put any constraints on it, then likely it would just turn off all the air, turn off all the pumps, and you would have no performance. So basically you may want to say, I want to hit a certain effluent target, but beyond that, do the best job you can in terms of energy reduction. Maybe you might want to bound a couple of things that are typical parameters that are in certain comfortable ranges, that the mixed liquor must be above a certain threshold or the SRT must be within a certain range. You can do that by applying a penalty function to the objective function based on those values. So the idea here would be, so say, for example, you want the mixed liquor to be at least above a certain threshold. So what you would do is add a term to the objective function that basically said, if mixed liquor is below, then we just add a big number onto the objective function. And then that number then will tell the optimizer, no, if I'm trying to minimize things, adding a big number is bad. I'm going to go away from that place where mixed liquor has fallen below. And it'll automatically kind of hard bound that particular region such that it doesn't want to go there and have a low mixed liquor. Right, okay, so we have set up in GPSX 2 or 3 different tools that you can use and do them in different ways. And so I wanted to cover the various options that we have available, and then we'll show you some of those live in action here. So we essentially have 3 different tools. We have what we would call our regular simple time series optimizer tool. So it is this button right here on your dashboard. So I'm showing you what it looks like when you're in modeling mode at the moment. You can click on this menu and go through the process of setting up an optimization for the first time. And you'll see that we have this time series optimization. Then we have also the dynamic parameter estimation tool that allows us to do optimization where things are going to change over time. And despite the fact that it says parameter estimation right in the name of it, it actually can be used for process optimization as well. And in fact, that's what it gets used for most of the time. And then we also have, now that we have this connection between GPSX and Python, we now have another tool called a data-driven optimization tool. So it actually runs in Python. And so in that case, you would use the Python tool, load up this script. And this is a much, much more detailed, much more powerful optimizer it takes a much sort of more global approach to looking at what's happening. And so we're going to show you an example of that one today as well. So the good news is if you want to know more about these in detail and you would like to actually play around with them yourself, if you go to the help menu and go to the tutorial guide for GPSX, each of these things has its own tutorial. So you can load those up and play around with them and use them, understand how they work and see how to set them up and play around. They are actually an extremely interesting process and was really good fodder for putting a webinar together today. Okay, so I'm going to start with the simple one first. The simple optimizer tool, it's time series, so you're going to run either just a steady state analysis, but typically we would want to run some sort of dynamic analysis or dynamic run a little bit. And we want to use, it uses the Simplex method it's a gradient method to try and use this sort of search routine to find the best set of parameters by looking in the most downhill direction. And what I mean by that is the optimizer will automatically run several times at the very beginning of the process, trying out different parameter sets, and then it gets an evaluation of the objective function that you have defined, and says, okay, what is my cost when I run it this setting? And then I'm going to change it and run it again and run it a third time or a fourth time. And then what it does is it looks at all that initial guesses that it did, and it says, okay, which one of these is the best one? Which is the one that has the lowest energy cost? And it looks at it and it says, okay, that's the downhill direction that I need to go. And so it kind of moves in that direction. It makes another guess over there and then another guess. And it kind of travels along the surface of the objective function. And occasionally it might sense that it needs to turn left or right, or possibly even back up and go in a different direction. And that's what's happening when it's running its consecutive sets of simulations. It's looking to find how I can get the best objective function. And it'll just keep going until eventually it converges to an answer. So this basically will be a converging to an answer that's the best answer that it can see. But I put that on the slide here just to emphasize that it is not necessarily the global best answer, but it is the best answer that it could see during the path that it took. Now, hopefully those two are the same thing. It's going to go in the best direction that it can, but it is possible for it to kind of get hung up in what you would call a local minimum there, like in a spot where it kind of took the best path it could and it didn't see any other more downhill area to go to, so it's going to stop there. That might not necessarily be the globally best answer. So the way to deal with that is actually try starting your optimization from a couple different locations, a couple different initial settings of the parameters. If it always converges to the same answer, then you know you're good to go. When you get to the end, once it's converged, you now have a value for each one of the parameters that you've put up there. So you have an optimal data set, and this is the one that is going to be the best setting that you have. Now, my experience over the years using this, over all of my career, is that it works really well for up to 3 parameters, up to and including 3 parameters. The reason it has that a little bit of that limitation is that it's doing this search in sort of an n-dimensional world, where n is the number of parameters that you're working with. So what that means is if you go to more and more parameters, like technically it'll work if you try it. You can put like 7 or 8 or 10 on there if you wanted to. But the thing is, it's then sort of searching in a 7-dimensional space. And as you go up in dimensions, it becomes sort of exponentially less efficient, and it's got more space that it has to search. So in a completely practical, like from my experience kind of point of view, I never go above 3 because 3 is kind of the best that it can handle. And that's why we have DDO and other things that handle higher dimensions much better. Okay, so that's our regular time series simplex method that we have. Now, the DPE tool is doing basically exactly the same thing, but it's going to do it dynamically. And what it does is it basically chops the simulation into these little time windows. And it does an optimization sort of piecewise on each of these things, one after the other. So what it does is for this little one window, it'll do the optimization. And then it gets to the end and it says, okay, this is the best thing. And then it uses that as the starting point for the next window. And then it optimizes to the data points, only the data points it sees in that window, et cetera, et cetera. And it keeps moving along, and it's producing a time series of answers. So you get a set of answers, a time series of optimal values, not just one value for the whole run. And this is great because what it does is it lines up the best setting of that one particular parameter for the data points and the model activity that it was seeing at that particular period of time. So this is much more advanced in its application and in its interpretation of how you could end up using it. So if you imagine, for example, if I was doing something with a wet weather event and I had some flow splitting or step feeding or some other parameters that I was adjusting, if I was using the other simpler method, it would basically just give me one answer. Just turn this on and do this number while the storm's happening. But in a situation with this DPE tool, you could actually see like, okay, here's every hour you should change it to this other new setting. And that gives you kind of like an optimal setting throughout the entire length of the event. Okay, and lastly, DDO, as I mentioned before, data-driven optimization, is a much more advanced tool. Basically, what it is doing, it is a Python program and other tools that we have built into GPSX, where you set up, some familiarity with Python is required in order to set it up properly, but it has a more wide range of features that are available in it. And what it's doing is it's actually running a large, more global analysis of the area in which you want to do your optimization. And it generates sort of a knowledge and an understanding, a database of relationships between the objective function and the parameters themselves. And then it uses that to do it to do the optimization going forward. And it's much more powerful in the sense it can handle higher numbers of parameters and so on. So in the latter part of the webinar today, we're going to show you what that looks like, and you can also play around with it yourself if you have the GPSX Pro Plus license by doing tutorial 18. Okay, so I'm going to show you first of all how we set up a time series or DPE optimization in GPSX, and then I'm going to go through doing one from my desktop. So for the GPSX setup menu, if you have to be in modeling mode to start, and you click on this little optimization button, and then you'll get the opportunity to start the optimize setup window. This is a little menu, a wizard, I guess you could say, that takes you through steps and helps you make all the choices that you need to make in order to set up the optimization. So the first thing you're doing in the first step in the process is choosing your targets for the objective function. So you can scroll through this menu here. This will show you all the objects that you have available and then the outputs that are eligible to be included in your objective function. So in this case, we're minimizing total nitrogen, so that's been checked off. And you can select one or more of those, and then they'll show up in this menu here. And then you click Next, and it'll take you to the spot where you can then specify, okay, what variables are we going to be adjusting? What is the input parameters that we want GPSX to take control of and tell us what the best values are? So you can go through those ones as well, select the ones that you want. They will appear up here. And then a number of settings for how the optimization is supposed to proceed. So first of all, the way that you are going to force the objective function to move. So this would be minimizing something, maximizing something, or fitting it to data. There's also whether you're doing the time series or the DPE is selected at this point in the process. And then there's some measurement here of how we calculate the difference between what the model is showing and what your objective is. And to be honest, for most process analysis, you don't really need to make an adjustment here. Any of these settings will work well. However, when you're fitting to data, you may want to have a little bit of control over how you calculate those residuals, the difference between the model and what the data said. And then lastly, running a little bit of a dynamic simulation. We actually have to run, even if we're using a steady state answer, we have to run a little bit of a dynamic simulation because that's how we go about calculating the objective function. Then you hit finish. And then what it does is it sets up all of the things that you need in the model. It constructs the objective function equation for you, actually sets up some graphs and sliders for you. And let's just jump right in and do that now. Oops, sorry, I jumped off my slides one too early. I wanted to talk about the actual question at hand. So for the first demonstration today, we're going to talk about a conventional activated sludge plant, this one showing here, which actually is doing alum dosing for phosphorus removal. And what our objective is here is today, we are going to allow GPSX to tell us the correct or most optimal alum dosage concentrations here while trying to reduce total dosage cost. So it will control how much is being dosed in our particular system. And we have a constraint that says we also need to make sure our effluent soluble orthophosphate is 0.1 milligrams per liter or less. Now, so that means it's not going to be able to just turn off all the chemicals in order to reduce cost, but it can't dose a huge amount either because it wants to try and reduce the cost. So there's like that nice, those two prongs there kind of pushing against each other, and it'll find the best setup for us. Okay, so here, in order to meet this, to put this constraint in place, we're going to use the EQI value. That's effluent quality index, and that's something you may or may not have actually ever looked around at in our effluent object in GPSX before. So I'll give you a really quick explanation before we go into the optimization here. The effluent object here, it doesn't really do anything, but it does calculate this index, which becomes very handy. So the first thing you can do in the input menu is list all of the limits that you want for the various parameters that you might, have a limit on at a wastewater treatment plant. So here I've set the soluble phosphorus limit at 0.1 milligrams per liter. And then you can do some weighting of that. So I actually have it set up. I put everything to 0 except for the soluble phosphorus. So this EQI value that we are going to be calculating is now calculated on the soluble phosphorus only. So the larger the concentration of soluble phosphorus, the higher this EQI value. Now, the key thing is it actually outputs what we call the net EQI. That's the thing that becomes really handy for optimizations. It is basically calculated on the difference between the limit and what's actually coming out of the plant. And so if you're below the limit, then it's 0. That's what we want to do, is we want to drive EQI to 0. If the phosphorus is going to be over the limit, then the EQI is going to be some large number. It's kind of the way of, doing that penalty function that way. Okay, so what I'm going to do is I'm going to take you through the process right now. Here's our optimizer button. I'm going to click on that. I'm going to go to optimize setup. And as I mentioned, that first thing is we want to choose the targets that we want to minimize. So as I mentioned before, we're going to be minimizing net EQI. So I go to the effluent object right here, and I'm going to slide down, and I'm going to say we want to do net EQI. That's one thing that has to go to 0 in order for us to make sure that we're meeting our requirements. And then the other thing that we would need to do is also the total chemical cost. And we're going to do it for the whole plant. That's why I picked the system menu, so that we capture the cost of both dosing points. So that's operating cost, total chemical addition, total chemical cost. So now we have these two things here that added together are going to be the thing we want to minimize down as low as we can get. Click on next. Now we're going to go and specify, okay, what are the things that the algorithm is going to have control over? So let's start with the chemical dosage at in the primary dosage area. We're going to do that on concentration basis. So close that one up. I'm going to go to the other one, do the same thing. Okay, all set. Now that's that page finished, and then we're going to move ahead and set some of our other details here. So the first one is I want to minimize that EQI and cost combination. Time series is what I want to do. We're not doing DPE yet. So time series, I'm going to leave it at absolute difference. That's fine. And then I'm going to make this 0.1 days just to make it go quick. Okay, so and then we hit finish. And then we can go over here, and you'll note, by the way, it actually has to rebuild the layout. The reason it's doing that is it's actually constructing the objective function equation that the optimizer then uses to sort of help drive everything in the right direction. Now, before we get going, I got a couple of things I want to just set up nicely here. One of them is the optimization parameters. You'll note that the things that I had checked off are now available up here. It added them for me. And this is a place where there's going to be minimum and maximum values that I want to deal with. So I'm going to actually change this so that it's 5. So in this particular case, what we're really talking about is, what is the maximum amount that we're going to let the optimizer put here for this particular value? So I picked 5 mostly because, that might reflect, an equipment limitation, or maybe just in a general sense, I don't want to let it dose too crazy because that would also affect pH and other things. So let's go with those minimum and maximums. And then over here on these two graphs, I just want to very quickly set these with the correct scale so that you'll be able to see what's happening. So here's our chemical cost in dollars per day. Let's call this cost. Now these two, by the way, when I went through the process of setting up the optimizer, these two graphs were set up here for me as well. And I want to change the properties here. This is our EQI. And I know that this is going to range up to about 5,000. And let's do that. Okay. So what this is going to be is, if I just run this without turning on the optimizer just yet, these two lines represent where we're starting from. So this is showing us a cost here of almost $1,500 a day in chemicals, and our EQO number is like 900 and something. So it's a bit of an arbitrary set of units that we're working in here, but just whether it goes up or down is the key factor here. Okay, so now what I can do is, if I want to see where I'm at, oh yes, I also wanted to point out that the effluent, let me just move this down. Our effluent soluble P, that we're applying this constraint on, is actually at 5. So it's not anywhere near what we need. Our soluble P limit is actually at 0.1. So we're going to expect to see this thing have to come down. Okay, so what I'm going to do is I'm going to turn on the optimizer, and I'm going to hit start, and it's going to start running some simulations over and over again. And you'll note here that EQI starts to drop, and the chemical dosage starts to go up, which makes sense. The optimizer is now making changes to these parameters. For the most part, it's increasing the amount of alum that we're dosing, and it's trying to find that best place. Well, the first thing you saw was that it went way up here because this EQI needed to be reduced. We needed the objective function was saying, we're having a huge penalty, let's dose enough to get rid of that first, and then we'll fine tune it afterwards, which is what it did. So it went up here, and then it kind of backed it off a little bit, and it kind of terminated here. And so now our cost is about $5,000 per day, and we can see the two dosages that we would expect to see. And there's quite a bit more in the second one here, in the secondary dosage, than there was in the primary dosage. So that balance between those two dosing points is what actually is required to meet that objective. So we got about 3 or 4 times as much in the second one as in the first one as a completely optimized setting. So before we move on, I want to run one more time here. I'm going to actually reduce the phosphorus limit. Instead of 0.1, let's make it 0.05. And then I'll reset this and run that again. And let's just see what number it comes up with this time, right? So now this is a much more challenging situation. So again, you can see the EQI here. This is our penalty function. It's pushing this down to 0. And then once it's down at 0, it's going to try and get away with the least amount of dosing that it can. Well, right away, you might notice here that this is pretty much maxed out at 5. So what that means is this is now dosing as much as we are allowing it to in the definition of our problem. And now instead of 1, where it was before, it's now about 3. So what it did was it said the most optimal thing I can do is max out the second one and then bump up the first one. And so it makes total sense. It's really interesting to sort of play around with these now. And of course, all of this is completely a function of everything that we have set up here. So for example, if I was to change the primary wastage, it would change the question a little bit. If I ran it at a different temperature and the biological part of it was sucking up a little bit more phosphorus, then that would change things again too. If we did it at a different influent pH, I'm sure that would change it as well. So these are all running under the current setup that we have. And so it's really, really fascinating and fun to play around and almost like do a sensitivity analysis of optimization on these various parameters that are going to affect this. Okay, so that's the end of that one. I want to pop back now to my slides and just introduce a next one. I did mention earlier that doing total nitrogen removal, so optimizing nitrification and denitrification, is also kind of a really fun and interesting thing to play around with. And in this case, we're going to put together this model, which shows a plant, an MLE plant. So we have an anoxic zone and an aerobic zone and an internal mixed liquor recycle here. For the optimization parameters is anoxic's volume fraction. So in this case, I'm allowing, or pardon me, I have fixed the total volume of these two things together but I'm allowing the anoxic volume fraction to vary. That's the thing we want to optimize. So if in the system it says we need more anoxic zone, it's going to take it away from the aerobic zone. And then also the internal mixed liquor recycle is also an optimization parameter here. So we have, again, 2 parameters that we are going to play with. And right now I want to reduce the total effluent nitrogen. And actually there are no constraints at this one, at least for when I start, right? And so let's take a look at where that puts us, right? And again, we're going to kind of do this as a steady state evaluation. Right, okay, so I'm going to load up my other example. Now, I won't go through the whole process again. I already did it, and I just wanted to quickly just show you what it looks like. We can see effluent total nitrogen here is our objective function. And these 2 things, which are custom parameters that I made in the background because I wanted the mixed liquor recycle ratio to be a function of the influent flow. So it's going to be like 1Q or 3Q or whatever. And then I wanted a fraction as a total fraction between those 2 objects. Okay, so there's those 2 parameters, and we're minimizing, and all of that is pretty much the same as before. Okay, so now let's run it once just to see where we're at to start. So here's our anoxic zone fraction. We're doing 50-50 split to start, which we know is probably not optimal, and an internal mixed liquor ratio of 0.5Q, which we know is also probably not optimal. It's probably too low. So that gives us an effluent total nitrogen of 12.4. So let's see what can be done to improve that. There we go. So what you see here now is that it really ramped up the internal mixed liquor recycle ratio. And what that's happening is it's basically saying I want to return a lot of the nitrate from the aerobic zone back to the anoxic zone so that it can be denitrified. And right now it's kind of converged down to a specific answer here. And you'll notice that these, even though it's kind of still fiddling around with some of these numbers here, you'll notice that it basically, this is 6. It's actually maxed out at the amount that we have that is the total high end here. So what's happening is that it is now optimizing to the maximum that we're allowing it to go. And I actually had been playing around with this a little bit earlier. If you put it up higher, it just basically takes as much recycle as you will allow it to have. If you put it at 10, then the answer comes out, it's optimal at 10. And it's showing us, by the way, also 44% of the total volume should be the anoxic zone. So what does that tell us? Well, that tells us that we're not, the reason it's like that is that we're not really constraining the internal mixed liquor recycle choice. You know, we're not saying, we're just saying it can't go outside this bound, but there's nothing that would ever incentivize the algorithm to pick anything other than the maximum. So one thing that we could do is, if we wanted to sort of make it a little bit more interesting, is to go back to the optimizer setup. And instead of just doing total nitrogen, let's add an energy component to it as well. So let's say, for example, if I go to that aerobic tank and pick the mixed oxygen, the aerobic tank, the internal mixed liquor recycle pumping, and then pick off the operating condition here. And then I'm saying I want to include pumping power in my set of things that I'm going to optimize. So that means it's not just optimizing total nitrogen now, it's going to optimize that at the same time as trying to optimize and reduce the amount of pumping energy that is required. So let's let that run again. So we're starting from that 12. You can see here, actually, this is the pumping one. It added that as a graph. Just let me very quickly change the scale on that. And then I'm going to turn this back on and let it go again. So starts out at 12 where we were before, and this starts to increase just like it did. But now that we've kind of mixed the optimization of nitrogen with the optimization of energy, it doesn't go crazy and just maximize out the internal mixed liquor recycle rate. It actually says, you know, I gotta keep that under control a little bit. Okay, so I'm going to stop here, and then I'm going to hand over the control over to Nick, and he's going to talk a little bit more about more advanced optimization routines, and then we'll come back at the end and answer some questions.
Okay, Thank you, Spencer. So as Spencer said, I'm going to be covering a bit of the more complicated optimization routines that we have in GPSX. So that obviously includes the dynamic parameter estimator that Spencer talked about, as well as the DDO optimizer. So today I'm going to start talking about the dynamic parameter optimization tool and actually just apply it to the chemical dosage for pee removal problem that Spencer has already talked about. So I'm going to be using the same layout that Spencer used. So basically the same sort of thing is going to be happening here. We're going to be looking at optimizing the alum 1 and alum 2 dosage rates. We have the same objective, which is to reduce the total chemical dosage cost, and the exact same constraint as well, which is obviously to keep the effluent soluble orthophosphate below 0.1 milligrams of phosphorus per liter. So the only thing different now is obviously we're using the DPE. So this is actually going to be a dynamic optimization. So now the optimizer is going to be able to choose a new dosage every 12 hours, and we're going to run the optimization for 2 days. So because we're doing this dynamically, we needed to also introduce a diurnal flow profile just to introduce some variability into the plant conditions, because if we didn't have this sort of flow profile, the optimizer wouldn't have much work to do because it wouldn't have to adapt to any sort of changing condition, and there wouldn't really be much of a point to even running a dynamic optimization. All right, so I'm going to jump over to the layout now. So this is basically the same layout as the one that Spencer was using with the same optimization setup. So you can see I have the 2 chemical dosages up here and the maximum phosphorus concentration. The only different thing now is that I'm going to go over to optimize mode here and go to type, and you can see that I have DPE selected here instead of time series because we're now running the dynamic parameter estimation. So I'm just going to turn optimize mode on and start running it. So immediately we can see how the DPE is different. You can see the simulation is only actually running up to 0.5 days, and this is because it's optimizing in chunks now rather than the whole thing. Because we've set the DPE time window to only 0.5 days. You can see that here in the DPE settings. Obviously, you can change this and set it to as long as short as you want, kind of just depending on how finely you want to tune, or you want the optimizer to, I guess, tune your plant performance. All right, so I'm going to jump over now to the effluent orthophosphate tab. Oh, and you can see there the DPE is finished with the first interval, and now it just moves on immediately to the second one. You can see here as well that it's basically hugging right there at the 0.1 limit, like we expect. And in the chemical dosage tab, we can see that it's just slightly changing the dosage each interval. It's not a huge difference, and it's still roughly in the same region as that first DP, or the first just time series optimization that Spencer ran, where he was just running for steady state. You can see the doses here. We have a lot in the secondary, and not as much in the primary doser, just as Spencer had. All right, so I'm just going to jump back over to the slides to wrap up this demo. So here I have the results of both a simple optimization and the dynamic optimization that I just ran in GPSX. So we have the chemical cost obviously on the y-axis, and then just the time and days on the x-axis. So this what I mean by simple optimization is basically this is just an optimization still using the time series tool in GPSX, but instead of like having different intervals like the DPE, it was just a 2-day time interval. So basically there was one set of chemical dosages used for the entire 2-day interval. It still was a successful optimization. It met all the constraints, but there was no flexibility to change the dosages at all. You can easily, like, quite evidently see that the dynamic optimization obviously did perform better. It had more flexibility to reduce the costs, and it did just that. Quantitatively, the cost reduction is the area under the curves, and we can just see that here. In total, we saved about $831 over the course of 2 days just by allowing ourselves to change the chemical dosage settings every 12 hours. So you can imagine that if we started changing the settings every 6 hours, every 3 hours, we'd get even more cost savings. It just kind of highlights a really cool aspect of the DPE tool and how you can kind of just use it for these kind of sort of cost-saving investigations of your process. All right, so now that we're finished with that one, I'm just going to move on to the final demonstration today, another operational example, but this time it's going to be using the dynamic DDO optimizer for plant-wide energy optimization. So we've put in a lot of work to kind of develop a framework around the more simple DDO optimizer that takes it from its more basic form and allows it to be used in a long-term dynamic optimization. And just before I get into the specific example of how we actually applied that to a plant-wide optimization, I'll first give a little bit more background on how DDO actually works, just so we're all a bit more comfortable about what's actually going on. So as Spencer mentioned, DDO can kind of be viewed as more of a global optimization. Although it's not 100% guaranteed it's going to find the global optimum, it does kind of create a bigger space to look at, so there's a higher chance that you can find a global optimum. And an easy way to kind of think about the DDO optimization, to conceptualize it in your head, is as optimization via mining a large database of simulation results. So the high-level methodology is basically that the DDO function generates statistical relationships that relate sets of values of the manipulated variables to values of the objective function and the constraints. And then these statistical relationships are used to suggest values of the manipulated variables with a high probability of improving the objective function. So visually, what this looks like is first the DDO simulator or the DDO optimizer is running simulations using randomized sets of manipulated variables and storing the values of the objective function and the constraints. And we call this the training set. And then it uses those results of those simulations and creates a statistical model linking those combinations of manipulated variables to the objective function and constraints. From there, it uses that statistical model to then suggest new sets of manipulated variables to check. And then it runs more simulations with that new set. So rather than the training set, we call this one the optimizer set, since it's actually kind of homing in on an optimal solution by running more simulations. And then this kind of just cycles through. So it updates the statistical model, linking combinations of manipulated variables to the objective function and constraints, goes back, uses its statistical model, and cycles through, basically until we get to some part where there's no further improvement in the objective function that can be found, and the optimizer will converge. All right, so just a couple points on some benefits of DDO. One thing is that it can be used dynamically or for steady state optimizations. It really just depends on how much effort you want to put into developing your Python code that actually drives the DDO tool. So the DDO tool is more of just an optimizer, and whatever you do with the Python kind of just limits how much you can use it. That kind of brings us to another benefit of DDO, which is that it's very flexible and customizable. So it can pretty easily be used to optimize 10+ parameters simultaneously. And it's really nice because of the integration with Python, you can get really creative with how you implement DDO, because you basically have all the power of Python and all those special Python libraries combined with the power of DDO and GPSX. So you can do a lot with this type of tool. Now getting into just, I guess, one drawback of DDO. It's not really a drawback of DDO as much as it is just a drawback of dynamic optimization in general, is basically that it can be time consuming just depending on how complex the problem is and the length of the dynamic optimization you want to run. So obviously if you're trying to optimize a month out for your treatment plant, you can't just run that in 30 seconds. It's obviously going to take a bit more time to run that, but that's not a problem that's just specific to DDO. It's pretty universal with dynamic optimization. Okay, so now actually getting into the example. So here we just have a MLE layout just set up for biological nitrogen removal. So here we just have the anoxic tank, and then it's followed by a plug flow tank with 3 aerobic zones. So in this case, we're going to be the optimized parameters. So the parameters we're going to be manipulating are the DO set points, the mixed liquor internal recycle, so this pumped flow right here, and the RAWS flow. So this one right here. And the objective of this is going to be similar to our other operational examples. We're just going to be trying to reduce the operating cost. And in this case, we're going to have a few constraints on the effluent. So we're going to be constraining the TSS to be below 20, the BOD to be below 6.5, and the ammonia to be below 0.5, and the total nitrogen to be below 8 milligrams per liter. And obviously, this one is also going to be dynamic. So the DDO optimizer is going to choose new operational settings every hour over the course of the 5-day simulation in an attempt to reduce the operating cost while meeting all these constraints. So finally, just to make it a bit harder for the optimizer, we kind of introduced a semi-irregular diurnal flow profile for the 5-day simulation, as well as a slightly decreasing temperature profile, just to kind of make it interesting and make sure the optimizer doesn't have just too easy of a job by just optimizing for a constant, or not constant, but a repeating diurnal flow profile with a constant temperature. Okay, so jumping now into this demonstration. So this is the layout that I was showing on the slide. And the results that I'm showing right now on these graphs are actually from a 5-day simulation using constant inputs. So these are not optimized results. So you can see here the DO set points over the full 5 days here, where 2 of the tanks had a set point of 2 milligrams per liter, and then 1 had a set point of 0. We can see the mixed liquor recycle flow was set to 3,000 meters cubed per day, and the RAWS flow was set to 2,000 meters cubed per day over the whole simulation. Here we can see the cost, so the total cumulative cost over the course of the simulation, as well as the instantaneous operating cost. And then here I'm just showing the 2 nitrogen species in the effluent, rather than all of them, just to make the graph a little bit easier to read. And one thing I wanted to highlight here is we have this total nitrogen line, the pink one. And if you remember from the slides, we actually have a constraint set in the optimization of 8 milligrams of nitrogen per liter. And you can see here this pink line going over this 8, or going over this 8 line here. So obviously in this non-optimized case, the total nitrogen limit isn't actually being met. So this is just something we want to keep an eye on when we run the optimized scenario, just so we can see and basically compare if the nitrogen limit is being met in that more optimized case. All right, so now I'm going to jump over to that scenario. So in this scenario, I have the results of the optimization stored in an input file, and they're basically just ready to drive the model. I'm not actually going to run the DDO optimization in this webinar, just because it would take a lot more time than what we have left in the webinar. I've already run it and recorded all those values, and they're in this input file. So that's what I'm going to be showing you today. I'm just going to start the run now. So immediately we can see all these settings start changing here. So these are all the values that the DDO optimizer gave us. And now they're driving the simulation. One thing to note as well is the cost graph here. So typically in GPSX, when we put data points on the graph, it's because we're trying to fit to those data points. But actually in this case, I've put the data points here as the cost from the non-optimized case, just because I wanted to be able to easily visualize how the optimizer is performing versus that. So what we're seeing with all these dots is actually the cost from the last simulation I was just showing. And here we can see that the optimizer's cost is just tracking below that, slowly increasing the gap in the cumulative cost. And over here, just tracking slightly below on the instantaneous cost. There's also these DO set points here where we're seeing a pretty big swing in the DO set points, which maybe you wouldn't typically operate at with that kind of swing at a typical plant. And that's kind of just highlights I guess a point with the DDO optimizer is that if you're not comfortable with something you're seeing, like this big swing in these DO set points, then you can just write some Python code to limit the swing. So it's a really nice thing about how the DDO is set up is that there's so many ways that you can use it. You can do a whole bunch of other calculations in Python on the side, and then still have DDO driving the GPSX results. I guess one more just to touch on here is these flows. So you can see that the recycle flow was decreased as well as the RAWS flow. So the optimizer obviously found that the flows in the steady state simulation were a little bit higher than necessary, and was able to run at these lower flows. And then finally, we see that the optimizer did successfully reduce the effluent total nitrogen. So this pink line here below 8 milligrams per liter without really any sacrifice in the ammonia removal performance. And that's pretty great to see. It basically overall just kind of shows that the DDO optimizer can be used to decrease the overall operating cost and improve or just match the performance from before. All right, so now going to jump back into the slides. Okay, so we just have a couple tips of kind of just to wrap up this webinar. So kind of the big overarching tip that we want to kind of just get across is that the optimizer really doesn't care about anything that's not constrained or part of the objective function. Now, Spencer showed this a couple times in his demonstrations and really, I think, hammered this point home well, but we're just going to reiterate it one more time. So you really need to be very careful that you define your problem correctly, because the optimizer is going to try to cut every corner it can. So, for example, if there's no cost included in either the constraints of the objective function, it's just going to increase the energy use as much as needed, even if it's only improving the objective function by the tiniest margin. It's going to do it because there's no reason for it not to. You have to always be telling it exactly what you want it to worry about. The same thing with the effluent quality. If it's not included, then it's going to sacrifice effluent performance in the name of either reducing cost or whatever else that you are trying to optimize for. So remember that you can use the EQI to constrain effluent targets. And again, there's not really a safety factor, so always remember to set your constraints accordingly. So even in like the MLSS tanks and the SRT, you want to make sure that if you're running a longer optimization that you're not wasting too much, and all of a sudden your SRT is way too low. You want to put constraints there just to make sure that you're covering all your bases. Okay, so now just some final thoughts. So the optimizer is a very useful and powerful tool to explore plant treatment behavior and to optimize processes for specific targets. And as we just were saying in the final slide or in the previous slide, it requires you to set up well-posed questions with reasonable boundaries and constraints. And often this is the most important step of the whole optimization, is just figuring out the question you want to ask and figuring out how to mathematically either put that into Python, put that into GPSX, just put it into whatever optimization tool you're using.